I am Mr. True. Okay, we're going to continue our discussion about setting up confidence intervals with using the T procedure, where we are working with sample means, but we only have, like realistically, we only have the data we collected from our sample or experiment. So we only have the sample standard deviation, not the population standard deviation. And in this video, I'm going to talk about a paired T procedure. When we talked about experimental designs, one of those experimental designs was called a matched pairs design. And we're going to learn how to make confidence intervals with data gathered from that matched pairs design. Now in experiments, that would be like let me just read this. Analyzing the mean difference between responses to the two treatments within a matched pairs of subject. So maybe like I want to see if there's a difference in recovery rate between those that drink water and athletes that drink, say, Gatorade. Well, I could match up players that have the same weight, the same age, the same speed, have historically, seem to perform the same, and let one drink Gatorade during exercise and one drink water, and then compare their recovery times. That's one way to designing matched pairs, but a lot of times, at least in my textbook, a lot of times matched pairs designs are where you put two treatments on the same subject. Maybe you have somebody do something left-handed or right-handed. This example is going to be talking about people taking, the same people taking a pre and post test and then comparing those numbers and keeping them to some degree organized. And that's what I've said here. Analyzing the mean difference between responses to two treatments applied to the same subject or unit. People don't like to be thought of as numbers, so if you're collecting data on people or if you're experimenting on people, they like to be called subjects. It just feels a little bit more personal, but it really doesn't mean anything different. Okay, so you would like to analyze the effectiveness of a class you are teaching, like statistics. I don't teach just one period, I teach multiple periods, and I've taught it year after year after year. Well, if I'd like to analyze the effectiveness of my class, so we're going to do this. We have each student take a pre-test and a post-test, and hopefully from that show an improvement in their grades. So we're going to estimate the true mean increase in scores for all students with 95% level of confidence. So maybe for some reason I didn't have every class take a pre or post test, or maybe we're saying, well, I've taught this for years, it's the same textbook, I've developed my skills, and so from now year to year, it's all effectively kind of the same effectiveness, hopefully this year more with the added benefit of watching some videos as a review. But the point is, we're going to allow a class to act as a sample and then use the results from that sample to make an inference about the entire population or all these students taking this particular class. And we're going to do that by measuring the grades of a pre and post test. So let's get on with the example, shall we? Alright, so we've got 10 scores recorded. The pre-test grades are 43, 71, 50, 53, 41, 62, 59, 67, 47, and 53. Then we take a post-test at the end of the course. Now, a matched pairs design is not just two groups of randomly selected, unrelated, or independent sets of variables. No, I want to track the pre and post test for each individual student. So it'd be very important if I'm doing this actual study to keep these numbers organized. So we have a pre and post test for each individual student and keeping those organized, because these scores, of course, are not independent of each other. It's the same person taking both. Now, when you have a matched pairs design, it almost looks like you have two samples, a group of data for a post test or pre-test and another group of data for the post test. Well, we don't actually have two independent sets of data, and we haven't even studied that yet as a class. Maybe you have reading this, watching this video, and you're just reviewing, but we have not yet. So this must be a one sample design, even though there's two treatments and thus two sets of numbers. And indeed there is, because in a matched pairs design, we only analyze the differences between the two responses, in this case the pre-test and post-test scores. So I'm going to subtract each one of these, and I've got my 10 differences between the pre and post test, and looks like a pretty effective class. All those grades have gone up, nobody went down, and whatever. Hopefully every class is like that, right, if it's effective. And we're going to set up a paired t-interval. So, again, you have 3 checks for confidence intervals. This is now my second or third video. So we need, so I didn't put them down ahead of time. We need an SRS, we need normality, and we need independence. So we need to assume these students represent an SRS. Might not actually be the case. Now, if I'm just a teacher, going along with my job, and I've got to happen to have a classroom of students, they may not really be a actual simple random sample of all the students that I teach. But if I have no control over the scheduling, this might be, a bit of a stretch to assume, but to be able to do the analysis at all, we have to make that assumption. And if they're obviously not an SRS, maybe take the results with a little bit of grain of salt. Normality. Well, when you're working with averages or means, you always have the central limit theorem helping you out if you're collecting, a set of numbers and averaging them together and analyzing that average. We always have the central limit theorem to help us out. But when you're given the raw data, make sure that during this normality check that you do actually show some graphical display of checking for that normality. We're not just going to assume it. We don't need to assume normality. We have all the numbers to look at. We can analyze that by making dot plots or stem plots or histograms and looking for that unimodal symmetric distribution. Unimodal symmetric is not automatically normal, so we also have something called a normal probability plot. I keep saying that, but it's been a while since we've actually done one as an example. I do, however, have videos posted about it. Now, with the central limit theorem helping us make sure that the averages, because we're not going to work with the raw individual data, but the collection of all 10 scores is an average, the central limit theorem is going to help make sure that distribution of averages is normal. So I don't need to really use a normal probability plot. I just need a histogram that is fairly symmetric and unimodal, and indeed we do. So with the diagram or the graph here for us to help us out, with the differences being fairly symmetric and unimodal, the central limit theorem will ensure the distribution of averages is approximately normal. And at the end of this video, I'll remind you again what the guidelines are for the central limit theorem and what constitute a large enough sample to make sure that your averages are indeed normal. So let's see what that confidence interval looks like, shall we? Okay, so anyway, third check, independence. Well, assuming that tests are taken individually and not cooperatively, and that we can assume that there is more than 100 students, 10 times the sample size, we should be okay with the idea of independence. So from one of our stats, with those list of differences we just had, we get an average difference of 29.4, the standard deviation of our sample of 8.09, the degrees of freedom is n minus 1 when you're dealing with t-distributions, n being the sample size, so 10 minus 1 is 9, and then when you go to the t-distribution, go to the bottom of that chart, find where it sets, what setup are we doing here? 95. Go to the bottom of that t-score chart, find where it says 95% confidence, and go up the chart until you get to a degree of freedom line of 9. Now, if your sample size is such that you don't have, like maybe the degree of freedom is 131, well, my t-table chart doesn't have a DF line of 131, so I would go up the chart and use a degree of freedom line of 100 just to be conservative. There is a DF line of 9 though, and so my critical value, my t-star value, is 2.262. So we are going to take the sample's average of 29.4, add or subtract 2.262 standard errors away from the mean. Oh, actually, I didn't write that out in this list. 8.09 divided by a square root of 10 is, I'm calculating the standard error of the mean. I just talked about that in my previous video, but you might not be watching both of these. When you use a sample standard deviation to calculate the standard error of the mean, it looks just like it did with standard deviation of the mean. It's the standard deviation divided by square root of n. It's just that you're using the standard deviation of the sample. So estimate plus or minus critical value times standard deviation of the mean, if you're using the words that are off your formula sheet on the AP exam. and I'm 95% confident that the true mean increase is between 23.6 and 35.2 points. Okay, the robustness of a T procedure. Robustness is the ability of a statistical test, or just process in general, like a confidence interval, to resist non-normalities in the data. Well, when we're working with averages, we have the central limit theorem to help us resist or take care of or handle any non-normality that we have in the raw distribution or data. So the normality of a population becomes less important as sample size increases. That's giving this central limit theorem more data to work with and make sure the distribution of those averages is approximately normal. And so we are working with means and the central limit theorem to ensure averages will be approximately normal if n is large enough. And again, the guidelines, this will be probably the third time I've included in my videos. If n is less than 15, the T procedure is safe, and that could be a t-test, which we haven't learned yet, or this T interval, confidence interval. The T procedure is safe if the data is approximately normal. It'll need to be pretty symmetric and pretty unimodal. If n is between 15 and 30, that's a pretty good size sample for the central limit theorem to work. So the data can not have any really strong skewness or outliers, but if there's some skewness and some non-normality, the central limit theorem is still going to make sure that your averages, your sample average, in this case it was an average of 10 pieces of data, that distribution of averaged values will be approximately normal. And then if the raw data, or if your raw sample has very strong skewness, then it's only going to be safe to do a t-test, or a T confidence interval if your sample size is over 30. So, I'm Mr. Tarrou. That is how to do a confidence interval with a matched pairs design or a matched T procedure confidence interval. Go do your homework. Woo! Bye!